Hi guys, today we're going to look at a problem involving two objects undergoing constant acceleration. So first things first, if you guys look at the course webpage, you should be able to download a PDF of the problem statement for this problem and also a PDF of the detailed solutions. So the reasoning here is that during this video I'm going to focus mostly on how you should set up this problem, focusing on the approach you should take, how you should think about it, and specifically the methodology you should be using. And so I'm not going to focus on all of the algebraic detail because that will be in the PDF solution, which you can follow along with yourself at home. So today's problem is going to be involving the equations of motion you guys learned in class. And so the first thing we want to do before we even start the problem is come to some understanding of what these equations of motion can tell us and why they're useful. So these equations of motion, if we look at them, we see they relate various physical quantities. So for instance, they have in them velocity final, Vf is velocity final, V naught here is velocity initial, A is an acceleration, T is a time, and Y is a position. So these are things that you learn precisely what they mean in class, and here is your toolbox. This is what relates those quantities to each other. And so the game we want to play here is to take these equations, figure out what we can infer from the problem. So we want to decide if we can figure out an object's initial velocity, perhaps it's given directly to us in a problem, and we want to figure out which things we know, and then from that we want to figure out which of these quantities can we solve for. So to do that, we're going to basically look at all four equations and see if we can find one that has all physical quantities that we know from the problem and only one that we don't know. So for instance, we might be given a final velocity of an object, an initial velocity, and then maybe we're given a time that it takes for it to undergo that motion. If we have all of those parameters, we can just plug those directly into equation number one here, this first equation, and then we can solve that for the acceleration. And so then that may be the final answer, or maybe that will help us get to the final answer. But in any case, that is sort of the way you'll utilize this toolbox. Okay, so let's look at the problem statement today, and that is as follows. Determined to test the law of gravity for himself, a student walks off a skyscraper 180 meters high. Stopwatch in hand, and he starts a free fall with zero initial velocity. 5 seconds later, Superman arrives at the scene and dives off the roof to save the student. Superman leaves the roof with an initial speed v naught that he produces by pushing himself downwards from the edge of the roof. He then falls with the same acceleration as any freely falling body. So the problem here then asks, what must the value of initial velocity be so that Superman catches the student just as they both reach the ground? Okay, so what we've just read is a problem given to us in very general words, in very general everyday language. And so the difficult part for a lot of students is to take that problem and mine from it and figure out what the precise physical quantities are. So for instance, in this problem they mention things like Superman pushes off the building and he catches the student. So the difficult part oftentimes is figuring out how those relate to things that we know how to deal with, so things like velocities, accelerations, and times. So the first step to any of these problems is going to be to draw out a diagram of what's going on. So I will draw the building here as a rectangle, and then this line here will be the ground. So once we have the building drawn, I'm now going to draw out the student here, and I'm going to draw him as a dot right here, and I'll label that A. So the student is sitting there, and then Superman, we remember, jumps off the ledge 5 seconds after the student. So we'll draw him over here, and we're going to label Superman S, and he'll be in green. And then it says that he pushes himself down towards the ground with an initial velocity of v naught. So that's what this v naught vector is. So the one other thing we now need to remember to draw is that these are both acting in a gravitational field, meaning that they both are experiencing an acceleration due to gravity. And so that's going to be denoted by this g vector right here. So once we have this diagram set up, we now look at this and we decide the next thing that we need to do is set up a coordinate system to make the positions defined. And so to do that, I'm going to draw a y-axis here, and I'm going to define the ground to be y is equal to 0. So once we do this, this sort of pins down this problem, and it defines very precisely that anything that's at the ground is going to be at y is equal to 0. And then similarly, I am going to define anything above the ground equal to positive y. So that implicitly defines that anything pointing upwards is going to be in the positive direction. So once we have all of this set up and we have our coordinate system pinned down, we can now do the physics, and that will relate to drawing a table. And this table will include what we know from the problem and what we don't know. So our knowns and unknowns. So I'm going to start by doing that for the student, which we've labeled A. So we're going to now try to mine from the problem and figure out which physical quantities of the student do we know. So the one thing it tells us at first is that he starts at rest. So that very precisely means that his v naught is equal to 0. So rest means initial velocity is 0. And then similarly, we know that he starts with an initial position, y naught, of 180 meters, which is to say he starts 180 meters above the ground, given our coordinate system. And then similarly, he ends up at y is equal to 0 meters. So these are three things we know. And then we know one other thing implicitly from the problem, which is that our acceleration should be minus g. So again, make sure you note this minus sign, because this is really due to the coordinate system that we've set up over here. This minus sign comes from the fact that up is defined as positive. So we see our gravitational vector pulls them down towards the Earth. So that must have a minus sign right there. So these are all things that we know. G is just 9.8 meters per second. That's a constant. So now we need to decide, is there anything we don't know about the student? And so if we look at these equations of motion, we can see that, for instance, we don't know the time. And this is something that will come in handy later on. So I'm going to write this down here as time is equal to the question mark. So now let's move over to Superman, who's in green. And we're going to draw some of Superman's quantities that we can get from the problem. So the first thing we can say is that the positions of Superman are going to be the same, which is to say y naught is going to equal 180 meters. Y is going to be equal to 0. So that says he starts at 180. He also starts at the top of the building, and then he also ends up at 0 meters, or he ends up at the ground. So those are the same as the student, and also the acceleration here is going to be the same as the student. And the reason is, as the problem said, these are both in free fall once Superman has made his push off of it. So what we now need to know is what don't we know. And so what we don't know in this problem is v naught. And this is actually what the problem particularly asks for. It says, what is the initial velocity that Superman must push himself off with to reach the student? So this is an unknown. And not only that, but this is the one thing that we want to solve in this problem. So once we can figure out what v naught is, we're done with the problem entirely. So what I would do to start is I would look at this column here and say, well, given these quantities, the ones we know and the one we don't know, are there any equations of motion that can directly solve this and we can be done? And if we look at that, none of these equations relate y naught, y acceleration to v naught directly. We need something like a time in there, and we're missing that at the moment. So when you're missing some information, when you don't have enough to solve directly for the equations of motion, you should look at what else you know in the problem that you haven't used yet. So in this case, that's the student over here. We have a lot more information, and we haven't used any of it yet for the student. So one thing we see is we don't know the time that the student's in the air, but that's something that we can actually solve directly for. So if you look at equation 2 here, the second equation, we see that all of these are known. We have them all written down here except for the time. So what we can do now to start and to finally get somewhere is we can see what the time that the student is in the air. So I'll call that t of student. So the time that the student is in the air, we can solve directly by plugging in our known y, y naught, v naught, and a, and then algebraically manipulating that to solve for t. So if you do that, you should get that t of the student is 6.06 seconds. So what that tells us is that the student is in the air falling until he hits the ground. It takes him 6.06 seconds. So now we want to say, how does that relate to Superman? And so we remember that Superman has what I'm going to call delta t is equal to 5 seconds. So that means that Superman delays his motion. He doesn't make his jump until 5 seconds after the student has already fallen. So now we need to take this into account. So if we want to figure out the time that Superman is in the air for, we can just subtract off that 5 seconds from the amount of time that the student is in the air. And so that will give us 1.06 seconds. So what this has told us is that it takes Superman 1.06 seconds to fall down to the, he has 1.06 seconds to fall down to the earth to catch the student. So this is really important now. We sort of now have the connection between the student and between Superman. So I'm going to write that now in this column here. We have now that t is equal to 1.06 seconds. And I will write the seconds here as well. So now if we look back to this column, we see we've just added information. So now we actually can solve the second equation of motion, which we couldn't do before because we didn't have a time. So if we do that, we plug in all of these known quantities again, we should be able to get to our final answer that v naught is equal to 165 meters per second. And so what this tells us is that Superman must push off the building towards the ground with an initial velocity of 165 meters per second to meet up with the student so that they're both at the ground at the same time. So now let's summarize what we've just done. We started by drawing a diagram, and then we defined our coordinate system on that diagram to pin down our positions. So then we decided upon what we needed to find and what we knew. So what the quantities that were known and that were unknown were. Then we used the equations of motion to first determine the amount of time it took the student to fall down to the ground. And then we remembered that there was a delay of 5 seconds for Superman to start his motion. So then we subtracted off the time that Superman was delayed and thereby found the amount of time that Superman had to reach the ground in order to catch the student. This time then we used, again with the same equation of motion, and we then found the required initial velocity. Okay, I hope you guys found this video useful, and I hope you guys learned a little something about objects undergoing constant acceleration, and about how to utilize these equations of motion that you learned in class. So if you guys have any comments about these videos or any ideas for improvement, please leave those on the course webpage. There should be a relevant section where you can do that, and we'll check that regularly. Thanks for watching.